Hello. We're now here talking about universal gravitation. Okay. So now in the last video, we looked at centripetal forces. And centripetal force was a net force. I knew you'd be able to say it. All right. So net forces mean that we have acceleration going into the center. And this is where we started to go into what does this look like on a much bigger picture, and what if the two things don't have a physical connection in between them. Now this is where Isaac Newton kind of looked at this, and he developed this law of universal gravitation. Okay, so now let's look at gravitational force. Okay, first of all, we have an object here, this is our Earth, and we have the moon out here. So now there's a connection between those two, and we know there is definitely a connection between those two. The moon kind of orbits around us, and it's like there's a tether between the two. So it's like there's a string that's connected between them. So I drew in a line that connected them, and this is now what we say is the force of gravity. Okay, so now there's this, and gravity is a field force. There's no contact between it. So if you go back to when we first introduced forces, they said there's contact forces and then there's non-contact forces. Gravity is just a non-contact force. All right, so now Newton said, I'm studying all this stuff in motion, and I've got a kind of idea of how the planets work, or how two objects can be attracted to each other. And that's really what it was about, was the fact that he said any two objects have an attractive force between them due to their masses. Now he published this in 1682 in a book. An interesting side note is he was accused of plagiarism. So he had to kind of defend his work. Of course, he then said that this is the root of what he was saying is that this force of attraction between the two objects is going to be proportional to the product of their masses. So in other words, if we have big masses, we have bigger force. If we have smaller masses, we have smaller force. So it's the product of the two masses, and it's an inverse relationship to the square of the distance between them. So the closer the two objects are together, the more force you have, but the further you get away, the less force you have. That's the inverse part. And it's an inverse square law. So in other words, if I get if I double the distance in between the two, I actually get a quarter of the force. Okay, it's an inverse square of that force. Okay, now he came up with this whole concept. Okay, that's what he really was about, was coming up with this concept. We couldn't put this to actual practical application numerically until 1798, when Cavendish came out, and he actually was able to do an experiment and determine things like the mass of the Earth. Okay, and so we had to have some technology advancements, and so it's about 70 some years or so afterwards when the experiment was done. So we're looking at a stretch in time between when Newton first came out with this and when we were able to calculate this. And really this is what Cavendish came up with, was what's the value to the G. And the G is, this G in our equation is the universal gravitation constant. Okay, it's one of those physical constants that we have in our world that we've now discovered. So we discovered that. We published it, 6.7 times 10 to the negative 11th. The units on it, newtons meters squared per kilogram squared, and we're going to see how that's going to kind of cancel out as we go through. So again, Newton came up with the concept, okay, and Cavendish came up with the constant, so then we could actually figure things out. So now if we wanted to figure out the force, okay, the force due to gravity between these two objects, we need to know, like, what's the mass of the Earth, what's the mass of the moon, and what's the distance between the two. Okay, with this we could then figure out how much force there is, attractive force. Okay, so now let's put this to a little practical sense here. And this is what this really means. Again, the way Newton wrote it is he said, all objects have an attractive force to each other. Okay? So in other words, if you're sitting next to a person right now, you have an attractive force to them. And so we're looking at it in the sense of, okay, I've got two people. Okay? One has a mass of 50 kilograms. The other one has a mass of 75 kilograms. They're sitting on a nice bench together. Okay? It sounds kind of cozy. And they are have an attractive force between them. Okay? Because they have masses and they have a distance. That's what Newton was saying. So now we could actually figure out what is that magnitude of that force. So in other words, what is the force of attraction between these two people based on their distance that they are away? Okay? So I can set this up. This is just a basic problem. I'm going to use the formula. It's 6.7 times 10 to the negative 11th newtons meters squared per kilogram squared times, now mass of person 1 is 50 kilograms. Oops, kilograms. Mass of person 2 is 75 kilograms. And the radius between the two was 0.5 meters, and I need to square this. Okay? So now I got to reach over and grab my calculator. All right. So now I'm just going to set this up. I'm going to take 50 times 75 divided by 0.5 squared, and then I'm going to take that times 6.7. Now this is where I'm using my scientific notation. 11 negative. Oops. Let's try negative 11. And I get 1.005 times 10 to the negative 6. Okay, what does that mean? That's 0.123456005. Now, what's the units on this too, by the way? That's the other thing we want to look at unit-wise. I have a kilograms, I have a kilograms. Kilograms and kilograms gives me kilograms squared. I have meter squared, I have meter squared. Oh, well, it's the standard unit for force. It's a Newton. So now I have that much newtons of attractive force in between the two people. Okay? Now, that's not a very big force. Okay? It's not a lot of attractive force. It's not like you're going to see a person, you're all of a sudden get drawn into them where you're going to collide into them, okay, because the force isn't great enough to pull. You actually have some other forces that are playing on you. So in other words, if we were looking at it from a free body diagram standpoint, here's my one person sitting on the bench. Okay, here's my other person sitting on the bench. They have attractive force between them, but there's a much bigger force that's attracted to a much bigger object, the Earth. So in other words, your attractive force to the Earth is bigger, much bigger than the attractive force that you have next to the other person. So we never even really notice that force, okay? The laws of attraction, or the force of attraction, is very, very small, which for some of you might be an okay thing. All right. So now, how do we use this? Okay, let's find a practical reason for learning about this. And this might be the fact that everybody here has television, and some of you really like to watch television through a satellite service, okay? A satellite service television is called a geosynchronous satellite system. What that means, geosynchronous, means that the satellite itself stays fixed at a position above the Earth, okay? So in other words, this satellite has to be right there, and when you aim your dish, okay, your satellite dish, you're aiming it directly at that satellite, and we don't want that satellite to ever move out of that position. If you did, you lost your reception, okay? And so that's really what we do, is we say, as we orbit around, so as the world turns, our satellite stays right in a position above us, okay? And so that's kind of what we're looking at. So I should have asked DirecTV for a sponsor for this video. Anyways, so now we're looking at putting that satellite in position and keeping it there. Now what this means is that the satellite only has kind of one force, okay, that pulls at it towards the center. And that's this force of gravitation, okay, this universal gravitational force. So in other words, our force due to gravity, or gravitational force, okay, if I said mass 1 is the satellite, and mass 2, I'm going to use a capital M with an E for the Earth, is our force of attraction between them. Well, that's the only net force being centripetal force, that's going to hold it in place. So in other words, my centripetal force is nothing more than Fc, okay? And so essentially we're saying that the gravitational force is equivalent to our centripetal force, and that's what's going to keep it in place. Now, there's probably a position, okay, a range at where this is going to work, but we have to keep in mind that Fc is, again, a mass, okay, mass in this case of the satellite, times some centripetal acceleration. And remember, my centripetal acceleration, I have two different ones that I could use. I can use Vt squared over r, or I can use r omega squared. And I need to kind of know something about how I want that satellite to behave, okay? If you think about it, it's a geosynchronous satellite. So in other words, it has to make the exact same number of revolutions as the Earth would in the same amount of time. So I'm going to actually pick this one because I want to talk about it in terms of revolutions that it's going to make. Now the Earth makes one revolution in 1 day. Of course, 1 day is 24 hours. And 24 hours, if you change 24 hours into minutes and minutes into seconds, is actually going to be 8,000 or 86,400 seconds. And if I change my from one revolution to 2 pi radians, this is my angular speed. Okay, so I do have an angular speed that I can look at. Now, the mass of the satellite is the mass of the satellite. So this mass here and this mass here can kind of cancel each other out. So my overall equation is going to come out to be G mass of the Earth over radius squared equals my centripetal acceleration, which is r omega squared. Oops, and I'm going to replace omega squared with 2 pi over 86400 quantity squared. Now again, ideally, if we know G and we know the mass of the Earth, and I'm going to know those values, so this is 6.7 times 10 to the negative 11th newtons meters squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilograms. And yeah, I just know the mass of the Earth off the top of my head. Oh, I went to Google. Okay, so again, there's the mass of the Earth, and now I'm going to bring this over here. So that's going to be equal to now my radius cubed, and I'm going to bring this piece back over to the other side. So I'm going to divide this now by the 2 pi over 86400 seconds quantity squared. And so now I'm going to end up with something that's going to give me what r cubed is. Of course, mathematically, I just take the cube root of this. Okay, and so then r comes out to be, and I'm trying not to write on myself again. I hate when I do that. 4.23 times 10 to the 7th meters. Okay, now what does that mean? Okay, it means that that's how far up above the center of the Earth the satellite has to orbit, and it'll stay in that orbit all the time. So there's kind of a nice little range that we work with, and we put satellites up there, and that's what we do. Now that satellite has to move at a set speed, okay? So there'll be a tangential velocity associated with that. We're not going to go ahead and finish that today. I just wanted to bring up the satellites And hopefully you kind of got a good understanding now of Newton's law of universal gravitation. So until next time, good luck.